Okay, so in class, we finished talking about what we looked at was the harmonic series, right? The 1 over n. And then we saw 1 over n squared. Now, 1 over n diverged, but 1 over n squared converged. So I want you guys to make sure you check out the harmonic series video that I've posted in the module on Canvas. Take a look at that, watch through it. It's not very long, but it does a really good explanation of how that 1 over n is adding numbers that are kind of getting closer to 0, but not fast enough. So the difference between that 1 over n and 1 over n squared is how fast they're approaching 0, which makes them either converge or diverge. So check out that video. And then also watch the support videos that go along with these integral and p-series tests. So now we're going to move on to the p-series. So a series of the form, the sum of n equals 1 to infinity of 1 over n to the p is called a p-series, where p is a positive constant. If p equals 1, the series is called the harmonic series, as we saw. The general harmonic series is of the form of the sum of 1 over an plus b. Okay, so the convergence of a p-series, the p-series converges if your exponent p is greater than 1 and diverges if it's between 0 and 1. Okay, so let's look at some examples. I'm going to zoom in just a little bit there. Okay, so do the following series diverge or converge? So on A, let's rewrite this so we have an exponent. We can see what P is. This is the same as the sum of n equals 1 to infinity of 1 over n, and this is n and n to the 1/2. So 1 over n to the 3/2. So P is 3/2, which is greater than 1. So this one converges. Okay. On B, we could rewrite this as the sum of n equals 1 to infinity of 1 over n to the 1/2. So P is 1/2, which is less than 1. So this one diverges. Okay, so even though these terms in this sum for part B are getting closer and closer to 0, they're just not doing it fast enough, essentially. So in A, those values on bottom are getting bigger faster than the values on bottom for part B are getting bigger. So we're adding on part B, we're adding, yes, smaller numbers, but not small enough numbers for this to approach 0 or to converge to some other value. Okay, so that's what you're going to see in that harmonic series video that I posted. So example 4, determine the convergence or divergence of the series. We can use any method. This one, part A, is pretty easy, right? We know that this is a geometric series. So we can use the geometric series test to prove convergence or divergence, right? So all we really need to do is find R, okay? A in this is 1. R is 1.075. So we're looking at, does the absolute value of R, which is the absolute value of 1.075, is it greater than 1, less than 1? This one's greater than 1, so this diverges. That's a pretty quick and fast test. If you didn't use the geometric series test, let's say we use the nth term test, we would take the limit as n approaches infinity of 1.075 to the n, which is just infinity. So this also shows divergence. Oops, diverges. Okay. Let's look at the next one. B. So we have 1 over n squared minus 1 over n cubed. Let's write this as a common denominator first. Okay. So if we got a common denominator, we would times this one really just by n. So I could write this as the sum from n equals 1 to infinity of n minus 1 over n cubed. Okay. From here, this is not a true p series as it's written right now. Okay, p series, we know the bottom is n to some p, which it is, but the numerator would have to be 1. So in this case, this isn't a p series test as it's written. So I'm going to do the nth term test. Let's see if that tells us anything. That's always a good first one to try, just like how I tell you to always try use substitution first. Nth term test is quick, it's fast, and if it diverges, it's conclusive. Okay, so we would do the limit as n approaches infinity of n minus 1 over n cubed, which is infinity over infinity. We need L'Hopital's rule. So we have the limit as n approaches infinity of 1 over 3n squared, which is 1 over infinity, which is 0. So in this case, this test was inconclusive. Okay. So again, the nth term test, it's not the most accurate test. It doesn't tell us all that we need to know, but it's fast if you're testing just for divergence, right? We know that this may or may not diverge, it may or may not converge, but it's for sure not just diverging because it's inconclusive. Okay, so we need another test to do this. We could try the integral test, that's always a good one, but we can also try p-series if I leave it written as it was originally. So if I come back up here to how it's written here, n equals 1 to infinity, I'm going to split this up, okay, to be two different sums. Because now this is two different p-series tests. Okay. So if I use the p-series test, we are testing for is p greater than 1 or is p between 0 and 1. And in both of these, p is greater than 1, right? 2 is greater than 1 and 3 is greater than 1. So this first piece converges. The second piece converges. So overall, this series converges. Okay, let's look at part C. Part C, we have 3 times the sum of n equals 1 to infinity of 1 over n to the 0.95. Super easy p-series test here. We don't have to rewrite anything. Whoa. P-series. Okay. So our p is 0.95. Wow. I'm saying and writing two different things. 5, which is less than 1. Okay. So regardless of that 3 out front, because this is less than 1, this diverges. Okay. And now for part D. Oops, I'm getting a notification. That's that black box. Ignore that black box. Hey, part D. We want to test the convergence or divergence of the sum of n equals 1 to infinity of 1 plus 1 over n to the nth power. Okay. Let's try the nth term test first. And if you are trying these other ways, check and see if you're getting the same result. This is not a geometric series, though. Okay, not a geometric series, so don't try that one. As it's written, it's not a p-series either. So really the only other one besides the nth term test would be the integral test that you would want to try. So now if I use my nth term test here, I'm going to write this as an equation. And the reason why is because I have an n as my exponent, and I want to try and get that out of the exponent position, which means I'm probably going to have to use a natural log. So I'm going to want to do the same thing on both sides of the equation, which is why I'm going to write this as y equals the limit, and we're solving for y. As n approaches infinity of 1 plus 1 over n to the n. So get rid of this this exponent using natural log. I have natural log of y equals the limit as n approaches infinity of the natural log, or n, times, actually write it this way. Nope, sorry guys, ignore my rambling you can't tell I'm rambling, but my brain is rambling. The limit as n approaches infinity of n times 1 plus 1 over n. Okay. So right now this is infinity. Okay, but let's rewrite this as the natural log of the limit as n approaches infinity. I left out my natural log, that's what I did. Obviously, there we go. I was like, it shouldn't be infinity. If you plug in direct substitution right now, this is infinity, but this is 1 over infinity, which is 0. So it's the natural log of 1, which is 0, which is infinity times 0. That's an indeterminate form. Okay. If I rewrite it, I can't use L'Hopital's rule with this indeterminate form. I need to get our infinity over infinity or 0 over 0. So that's why I'm going to rewrite this as the natural log of 1 plus 1 over n over 1 over n. Because now if I do direct substitution with infinity, I'm getting 0 over 0. And now I can use L'Hopital's rule. Okay, so I have the natural log of y equals the limit as n approaches infinity. The derivative of the numerator is 1 over 1 plus 1 over n times negative 1 over n squared over the denominator is negative 1 over n squared, which is really good for us. Those are going to divide out. So then I have the natural log of y equals the limit as n approaches infinity of just 1 over 1 plus 1 over n, which if I plug in infinity now, that makes this a 0, which is 1 plus 0 is 1. This is just 1. So the natural log of y equals 1. Raise e on both sides, so y equals e, which is not 0. Okay, So whenever we get a non-zero answer for the nth term test, it diverges. Okay. If you chose to do a different method, make sure you get a diverging improper integral. That would be the only other method, is the improper integral test, okay? So that's it for 8.3. Go ahead and finish writing in the notes. This assignment will be due next week, and we'll move on to 8.4 come Monday. And we'll have an opportunity on Tuesday. Thanks, guys.